Good morning and thank you for the opportunity to present my research. My topic is the impact of crude oil price volatility on airline operating costs using AirAsia as a case study. This presentation summarizes the background, methodology, key findings, model results, implications, and future direction. The main focus is to understand whether crude oil price volatility directly affects AirAsia operating costs, or whether the impact happens through operational factors such as fuel consumption and revenue scale. The main problem is that AirAsia depends heavily on aviation fuel, but crude oil prices are determined by external market forces such as geopolitical tensions, global supply and demand, exchange rates, and macroeconomic shocks. As a low-cost carrier, AirAsia must maintain load fares and cost efficiency, so even moderate fuel cost changes can affect profitability. The objectives are to analyze oil price volatility, study its relationship with AirAsia fuel costs, determine the impact on total operating costs, evaluate how oil price changes influence the airline cost structure, and provide useful recommendations for cost management. This research uses a quantitative design based on secondary data. The datasets cover the period from 2040 to 2025 and combines AirAsia financial operational data with crude oil and fuel price indicators. First, the data was collected from annual reports and global energy data sources. Second, the data was pre-processed by standardizing the variable names, cleaning numeric values, and handling missing values. Third, exploratory analysis were used to identify trends and abnormal periods. 4. Correlation and OLS regression were applied to test relationships. Finally, machine learning models were used to compare predictive accuracy and understand which variables are most important in explaining operating costs. This slide shows the descriptive trend between AirAsia aircraft fuel expenses and total operating expenses. Overall, total operating expenses are consistently higher than fuel expenses because operating costs also include staff costs, maintenance, airport charges, leasing, and other operating items. The highest operating cost is approximately 4.783 billion in 2018. While the highest fuel expense is about 1.876 billion, also in 2018. The chart also shows a major structural break during the pandemic period, especially around 2020 and 2021, when flight operations reduced sharply. This trend suggests that fuel cost is an important driver, but not the only factor explaining the operating costs. This slide focuses on the fuel cost share and correlations. Fuel cost share started at about 46% in 2014, dropped to around 5% in 2016, then increased again in later years. The highest point is around 55% in 2023, showing that fuel became a very large part of total operating expenses during the recovery period. The correlation metrics are positive findings. Revenue has a stronger correlation with total operating expenses at R equals 0.94, while fuel consumption is also strongly correlated with operating expenses at R around 0.857. Aircraft fuel expenses have a moderate relationship, with total operating expenses at R equals to 0.544. This means fuel matters, but operating skill and fuel consumption matter more than crude oil price alone. The OLS regression was used as a baseline model to estimate the effect of aircraft fuel expenses on total operating expenses. The coefficient is 0.8664, meaning that 1 million increase in fuel expenses is associated with about 0.866 million increase in total operating expenses. The R-squared value is 0.296, so fuel expenses explain about 29.6% of the variation in operating costs. The p-value is 0.067, which is marginally significant at the 10% level, but not at the conventional 5% level. This suggests that fuel is important, but the relationship is not strong enough to fully explain the operating cost by itself. After the RNI baseline, several machine learning models will compare using IMSE, MAE, MAPE, and R-squared. Gradient boosting produced the best result with the lowest IMSE of 485.48 and the highest R-squared of 0.6809. Random forest and ridge regression also perform relatively well, while linear regression and lasso regression perform poorly with negative R-squared values. This shows that AI's operating cost behavior is not purely linear. Machine learning is more effective because it can capture nonlinear interactions between revenue, fuel consumption, utilization, and fuel price variables. This slide compares actual operating costs with the gradient boosting predictions. The model successfully follows the broad patterns of the data. It captured the cost increase before 2019 and the sharp decline during the COVID-19 periods, and the gradual recovery after 2021. However, some deviation remain. The model slightly overestimates certain years and underestimates others. This is expected because the dataset is small and airline costs are affected by many factors not included in the model. The key point is that gradient boosting is useful for forecasting and scenario planning, but should be used together with managerial judgment. Feature important explain which variable contributed most to the gradient boosting prediction. Revenue is the most important variable with a score of 0.5021. This means that operating cost is strongly tied to an airline business scale. Fuel consumed is the second most important variable with a score of 0.3806, confirming that operational intensity and actual fuel usage are critical cost drivers. In comparison, Brent oil price, average fuel price, and aircraft fuel expenses have lower scores. This does not mean that oil price is irrelevant. Instead, it suggests that crude oil price affects costs indirectly through actual fuel consumption and operational activity. In conclusion, the study finds that the crude oil price volatility is relevant to AH's operating costs, but the impact is mostly indirect. The strongest cost drivers are revenue scale and fuel consumption. For AHL, the main recommendation is to improve fuel efficiency, optimize fleet and routes, review hedging strategies, and adopt predictive analytics for cost planning. For other airlines, the lesson is that fuel price forecasting alone is not enough. Companies must identify their own operational cost driver. For public transportation, the findings support the importance of energy efficiency, sustainable fuels, and reducing dependency on fossil fuel volatility. Future study can improve the model by including the hedging data, exchange rates, passenger load factors, aircraft leases, and comparing several airlines. Thank you.